is intended to determine the sending end voltage of the power system. So what do we mean by sending end? This is a common problem that you will encounter from time to time in this subject. Okay, that means that last time we during the lecture, okay, we were discussing that the main component of power system consists of the three subsystems called GTD, okay, generation, transmission, and distribution. So the generation would means that this is the source, right, of the circuit, and the distribution means the load, right. So these G and D are connected via transmission line. Okay, this is the medium that would link between G and D. So in most of the scenario, right, we need to compute, right, the voltage at the sending end or at the source of the system. Okay, because in power system, the ultimate goal of having power system is that we need to supply the load at the level that the consumer needed, right? So that means that the voltage at the load is normally fixed, or it is normally specified. Okay, the voltage at the receiving end voltage at the load, okay, voltage at the load is normally specified. Okay, you can see from this picture itself, because this picture is a simple representation of a power system. So on your right side, your VI here would stand for receiving end voltage. Okay, this is the receiving end voltage, where S standing from the sending end. So this is the sending end voltage. Okay, so as I said earlier, right, the goal of power system is trying to supply the voltage at the level that the consumer needs. So in this case, the problem suggests that the voltage at the receiving end is 10 divided by root 3 kV. So this is a single phase representation of the system. So this means that the system itself is three phase. Okay, and we assume that this three phase is balanced. So the main assumption is that we are dealing with a balanced or symmetrical three-phase system, and we analyze the whole system by using the per phase concept. Okay, we use the per phase concept. So this is the circuit of the single phase representation. So we just take one phase out from the three phase, and we analyze for just a single phase. That's why you see we have the voltage at the receiving end as 10 divided by root 3 kV. That means that the voltage, the line-to-line voltage of the real system is 10 kV, right? The real line-to-line voltage that you could measure from the system is 10 kV, and the current flowing, the magnitude, the absolute here stands for magnitude. So the magnitude of the current flowing from the source to the load, okay, is 150 amps. So this is the simple power system. So we have to make the assumption of the short transmission line. So this is the topic that we will also learn in this subject. So this is the simplest model of the transmission line. So the transmission line is represented by a single impedance for the case of the short transmission line. So in this case, the voltage at the sending end, okay, and there is the current flowing from the source to the load, and it creates the voltage drop across the line. Okay, so if the VR here is 10 divided by root 3 kV, that means that the sending end voltage is greater than this much. Okay, 10 divided by root 3. 10 over root 3. So the Vs here must be greater than this value, okay? Otherwise there is no voltage drop across this. And since the transmission line is an RL element, right? So at the receiving end of the transmission line has an inductive load is present, and the current lags the voltage by 36.9 degree. So that means that when we use the voltage at the receiving end as a reference, okay, the current that flows in the transmission line must have the phase angle of negative, okay, 36.9 degree. Okay, so now you can see that the phasor of the current here would be 150 amps and the angle of minus 36.9 degree. Okay, is it clear? Because for this single phase representation, okay, wherever we know the voltage, okay, we normally put the reference to the voltage that we know in the circuit. Okay, this is the concept that you should have learned from the circuit. Okay, that's why we can say the current lags the voltage. Okay, so you have to put the voltage as a reference. So now it means that this is VR and the I just lag the VR by the angle of negative 36.9 degree, right? That's why we have the lagging power factor. The situation is shown in this figure. We want to calculate the voltage at the setting end. Okay, now it's clear. Everything is all given, right? So and this is the concept that very easy for you to do it. Okay, now you know that you want to compute the Vs. So in this case, the Vs is the voltage at the source that must be greater than the voltage at the receiving end plus what? The voltage drop across the line, right? So the VR itself, Vs is VR plus, right, the current phasor times Z, right, which is R plus JX. Okay, the Z is here, Z is R plus JX. So by computation, right, VR here is 10 over root 3 and the angle of 0 plus I is 100. Now you have to take care of the unit a little bit because this is in kV. So when you plus the voltage drop, right, if you don't convert this to volts, so this voltage drop must be in kV as well. So you have to make sure that you get the kilovolts or the 1000 times the basic unit. So that means that now you see the current, your current is given in the current is given as amp. So if I need to convert this to kV, so I should change this to kiloamp and multiply by the Z in ohm, right? That's how, okay, you will get the voltage drop in kV. So if I change this to kiloamp, right, it becomes 0.15 and the angle is unchanged, okay, because you just divide it by 1000 on right, you divide this by 1000 and the angle is unchanged. So the thing is, you know, you can put in this way 0.15 kiloamps times the C is given as 4 plus J7, but if you convert this, this is given in terms of the rectangular or Cartesian coordinate. Okay, you could re-express this in terms of polar form. In polar form, that is 8.0622. The angle of you can round this a little bit, but I prefer to use it with the some decimals. Okay, with the angle of 60.25. This is ohms. So you multiply, okay, the I, which is here, I 0.15 angle of 36.9. Okay, and you multiply this with the you multiply this by the Z here, which is 8.06, and angle of 60.25. Okay, this is in kilo amp, this is in ohm, so the multiplication you should get in kV. Okay, now the nice thing about having this two quantities in polar form is that you could multiply the magnitude together, and the angle you get the sum of these two. All right, so I will leave this to for your own calculation, so you would get the polar form wherever you answer the voltage. Okay, you need to answer in polar form, because your meter, when you get you measure, you want to measure the voltage. Okay, you measure the magnitude of the voltage, right? We never get the real part or imaginary part. So from measurement point of view, okay, we are interested to know the right voltage magnitude, or the magnitude of the AC signal. So when you answer, you must, okay, I reiterate that you should answer in polar form only. Okay, whenever we have the complex calculation like this. Okay, and the angle should be 3.982 kV. Okay, this is Vs. Okay, this is the calculation. So if you want to see in terms of the phasor diagram, okay, let me draw the phasor diagram for you. Okay, now you see from the equation that describe this the circuit is like this. Okay, the Vs is equal to Vr times the voltage drop. So the reference or the zero angle, right? Because when you draw the phasor diagram, you draw in the complex plane, right? You draw this in complex plane. So your Vr is a reference. So the Vr is here. So right, and I times Z, your I would be, it's a lagging power factor, so this is here, this is I, okay, and Z, if you decompose this, is R plus JX, okay. Multiplications of I times Z, that means that you have the I, right, you have magnitude of I. Of course, this is the you have to multiply I by, with the real part and the imaginary part. Okay, in this case, all right, you multiply, when you multiply I with the real part, so you multiply this, you never change the axis, right? The angle will be I times R, because you have the I here and you multiply by R. Okay, you will get the parallel vector to this. This is I times R. Okay, and when you multiply I with the JX, now you can see that the J, if you convert this into polar form, the angle of J is 90 degrees. So basically, when we multiply, with the JX, for example, okay, you will just shift the vector by 90 degrees. Okay, that is to create the perpendicular vector. Okay, so now you can see that this is for example, this is JX times I, right? Because the J here would create the 90 degree, okay, difference with the multiplication with the I, okay, and this is what I times R plus, right, JX times I. So this is the sum of these two guys. Okay, this is the sum of I. This is I R plus JX. So this is the voltage drop across, right? This is the the delta V, the voltage drop across this transmission line. Okay, so basically this is the delta V. Okay, VR plus the delta V here, that is equal to the Vs. Okay, this is the how you draw the what we call the phasor diagram. Okay, by this course you should be able to draw this phasor diagram. All right, so this is the example. So this is clear. I hope this is clear to you. But the concept that I will discuss after this, okay, of course this is the first time that you may encounter this this kind of calculation. Okay, I will just play around with you first. Okay, I will just show you how to use this what we call per unit calculation for this particular problem. If you don't understand, that's fine. That is very normal. Okay, we will discuss this in very great detail. I will try to make sure that you can get through this concept, okay, in a separate lecture. But let me push this example, or I will push this concept at this moment. Okay, and I will just try to show you that there is another way to, in power system to attack this kind of problem. All right, let me use the concept of per unit to solve this question. Okay, this is the next topic on per unit calculation. Okay, this is what we call per unit calculation. So basically we have, okay, I will redraw this problem a little bit. This is VR, which is equal to 1 divided by √3 kV, and of course when we say in this problem we can put the angle of 0 for this case, right? And this is the Z. Your Z was given as 4 plus J7 ohm, and the current flowing in this one is I. The complex quantity would be 150 amp, and angle of I should do it like this, 150, and the angle of negative 36.9 degree in amp, right? I will just go to I just use the concept, okay, and if you understand, this is very good. But if you don't understand, we will get into that, and I will explain it in another video. All right. The way I would do this one is called per unit. The per unit itself is it's a ratio things. Okay, it's a ratio that is used normally, to compare two things. Okay, when you want to compare 1,000 baht and 1,000 euro, okay, you have to convert this into a common unit. Okay, either you could normalize. Okay, you can change the percentage. For example, you change the percentage to Thai baht as a common unit. So you say that the Thai baht is 100%, or this is the ratio of 1. Okay. And 1,000 euro would be, 1,000 euro would be 40 times greater than the Thai baht. Okay, 1,000 Thai baht and 1,000 euro. The 1,000 euro is around 40 times greater than 1,000 baht. So this 40 times is called, if you use the base or the quantity of reference is Thai baht. So we say that the Thai 1,000 baht, and you use 1,000 baht as a reference, so this is called 1 per unit, or 100%. Okay, 1,000 THB. We're trying to compare 1,000 THB with 1,000 euro. Okay, so I will put the rough currency exchange. Okay, the exchange rate I would take like 1 euro would be approximately equal to 40 baht, for example. So you can say that we try to compare these two, all right? So you have to have the certain base, or a reference value. So if I'm a Thai person, so I prefer to use the Thai baht as a reference. So I will say that I will just give 1,000 baht as a reference. So I put reference. In this case, we call base of 1,000 baht. Okay. So I will say that I'm having with 1,000 baht, I have 100% of the base, or this is 100%, right? If we put the base to at 1,000 baht is 100% of the base, or it is a ratio of 1 because this is 1 times greater than the 1,000, right? So this is called 1 per unit, okay? Because we say that this is a unit of how many times greater than the base. So we call this 100% is equal to 1 per unit. All right. If we put the currency exchange to 1 euro to equip is about 40 Thai baht, right? So for 1,000 euro, it's about 40,000 Thai baht. Okay. And the base is 1,000. We specify the base as 1,000. So this is about what? 40 times, right? 40 times. In this case, 40 times we say 40 per unit of the base. Okay? Or what? It is for 40,000%. Okay? Not, is it 40,000? No. You just multiply this by 100, right? In terms of the whole score is 100. So this is 4,000%, right? Greater than the base. Okay, this is 4,000% greater than the base, or 40 times greater than the base. All right. So the reason I will just put in this way, the per unit means like this. Okay, this is what we call per unit, in short. Right. The reason why we use per unit here, because in power system you have several equipments as we discussed in the first lecture, right? When you handle with the system with different ratings, okay, you could also say you could also put the same analogy as when you compare the equal amount, equal figure of money with the two different currencies, right? You say that one transformer is big, but you are in transmission system, and you say your transformer is big, but this transformer, if you go to the higher voltage level, your transformer could be very small, right? Because the power is so great, it is so big, right? So in this case, you can also we use the concept of per unit to compare different quantities. So in analyzing in the use of per unit, you need to specify the base. Okay, you have to specify the base, because this is normalization. Okay, because the per unit itself is called the process of normalization. For those who do not understand the terms normalization means to convert this into the ratio or into the percentage, right? You need to compute the base. So this is the requirement for specifying the base in per unit. Okay, two quantities. Okay, when we say about the power, okay, you would think of power. Okay, you would think of power quantity, current, right? You would think of what? Voltage. You would think of impedance. Okay, these are the four quantities that you may think of when we talk about power, right? In power, okay. So because if you know the current, you know the voltage, the multiplication of these two, you get a power. Or the two quantities, voltage and impedance, right? You could also determine the power. Or the current and impedance, you can also find the power, right? Or you could also if current and the impedance, you could also determine the voltage. Okay, so the concept of power calculation lies in these four quantities. Okay, the concept, very important concept, is that in order to analyze the power quantities, you must know two variables. In order to, you must know two quantities in order to find the other two. Okay, this is the concept that you should have in mind. Okay, in power calculation, you must know two variables in order to find the other two. Okay, as you saw, or as I discussed earlier, you have to know two quantities. For example, you know current, you know impedance. Now you know the other two. Okay, but very big but. Okay, the quantities that we normally specify, the known variables, the known two variables, right? In per unit calculation, we should know power and voltage. Okay, these must be known for per unit calculation. Must be known. Okay, you may wonder why these two must be known, power and voltage. Okay, the reason is simple. We discussed in first lecture that the voltage is normally used as the criterion to specify the transmission level, right? Whether it is an extra high voltage, medium voltage, or low voltage. So the classification of the power system is done via the voltage level. So the voltage must be known for each of the equipments, right? And the power, okay, as we also discussed in the first lecture, power means capacity to do the work. Okay, so if you specify a certain equipment in power system, so you must know the capacity of that equipment itself, right? Because you want to get a transformer, you have to specify how big your transformer is, right? And at which voltage level your transformer is connected. So these two quantities must be specified beforehand, right? And the current and the impedance can be determined afterwards. Okay, right? So the two quantities must be known. In this case, right, we want to normalize everything. Okay, we go back to this circuit. Okay, the circuits are specified. We say in per unit calculation, we say all these three quantities. We have Z, we have impedance, we have current, we have voltage, right? So these three quantities are given in real quantities, in the original units, right? For example, C is in ohms, current is in amp, voltage is in volt, right? These are in real quantity. Okay, real quantities. So real quantity, the quantity, the value is takes the original unit. Okay, the key concept is that you have to change these quantities in the real quantities, these real quantities, to be in percentage. Okay, how would you change this to percentage or to per unit? Okay, the idea is the same. You see, when we want to change the 1,000 baht to 100%, meaning that you have to take the base. Okay, you have to take the base, and we say how much 1,000 baht, right? How big of the 1,000 baht compared to the base. Okay, so in this case it's the same. So we have Z, we have I, and we have V. So you have to specify the base for each of these three quantities, and then you could compute the base, and you can convert these three quantities into per unit straight away, right? So in this case, as you see, right, the voltage at the receiving end is 10 divided by root 3. So if I say that this is the 100%, or this is the 100% of the capacity of this load, because this is the receiving end is connected to the load, right? So if I specify, because you know the requirement that we already discussed, that we need to know voltage and we need to know power, right? So in this circuit, I don't have any other voltage level in this circuit, right? So I would just say that I want to take this VR to be at my 100% or 1 per unit here, okay? So that means that I choose, okay, V base, okay, the base of this circuit to be 10 over root 3 kV, okay. And now you can see that if I choose the base to 10 divided by root 3 kV, so this VR would be equal to 1 and angle of 0 per unit, okay, because I just divide this by this value, okay. And remember the base value, okay, the base quantities, okay, must be, this is very important, okay, the base quantity must be real, must be real. So why it must be real? Because you know, if you put your base in as a complex number, then you would change the phase angle, okay. If you put the phase angle, I mean, if you put the phase angle into your base, you would change the actual phase angle, okay. Now you see you have the V base, so now you could you know, convert this 10 divided by root 3 kV into 1 per unit, 1 and angle 0, right? Because this is this guy divided by 10 divided by root 3, this is the base, right? Base, that you change this to per unit, all right? Now we need to determine the base for impedance and the base for current. So I need to compute, right? We need to find, okay, Z base and I base, all right, C base and I base. So I re-emphasize here that when I write C base and I base without any underscore, right, these are in real, these are reals, right? So the C base and I base is very simple. I will do the I base first, because the I base here, okay, you must know the power, right? One of the remaining requirement is that we need to know voltage and we need to know power, right? So you know that the power is a multiplication of voltage and current, okay. Now we will specify like this. We use the apparent power as the power base. So this is so we use the apparent power, or S, as the base quantity, okay. So your I base would be, okay, the S base divided by V base, because S base is equal to V base times I base, okay. Now I want to choose, okay, again S base to be equal to a fixed, so a certain number, okay. So in this case I choose as a 1 MVA, okay, 1 MVA, because this is an apparent power. So I just I don't know how much the the power the base is, you know, but I would just use this base for the whole system, and we try to compute this that the power that available to the circuit is in how it takes how many percent of the base value, right? So in this case, if I take this SB to be 1 MVA, right, my I base would be 1 MVA divided by the V base. V base in this case is 10 divided by root 3. This is in kilovolts. So here it is the 173.2 ampere. This is my I base. So once I know that the I base is 173.2, I can convert this I, right, to be in per unit. I can change this to per unit quantity. So the conversion is done like this. Okay, the I, okay, is 150 divided by 173.2 ampere. This is in percent already. Okay, so I re-emphasize that by dividing, by changing to the per unit, right, you never change the phase angle. So the phase angle is the same, right? The phase angle is the same. After the calculation, this is the result. Okay, 0.866, and the angle is 36.9, and the unit changed to be per unit. Okay, the per unit means that doesn't have any unit, or it is unitless. Okay, because in this case, why it is unitless? Because this is m divided by m. The m just cancel. So the per unit itself doesn't have any, physical unit. Okay. So in summary, you can see that what we are doing here is that we are trying to change all the circuit quantities to be in percentage. Okay, and we compute this in percentage, right? So the last thing that you need to do is that you have to convert this C to be in per unit. So what I need is that I need to divide this figure by the Z base. Okay, now the Z base, we have to determine it. Okay, as a requirement is that we need to know S base and V base. Okay, these are the requirement. You need to know these two, and soon after you know these two, you can find I base, you can find Z base. So everybody knows that the S base would be equal to V base square divided by C base, right? V square divided by C, it is the power, right? Well, now we say in terms of the magnitude of the complex power, that is called apparent power, right? So now if you want to find Z base, so the S and the V are known, these two are known, we want to find the Z base. Okay, the Z base it's what? It is V base square divided by S base. All right, so the V base here is what? The V base here is 10 over root 3, okay, kV. Note that this is kV square. Now you divide this by S base, which is 1 MVA. So you can see that this is kV square, K squared, it becomes what? Kilo square become mega, right? So the meg up and down just cancels, all right? So now this is your S base in ohm, right? Now your Z base is 33.33 ohms. This is the S base. So now you can convert your C, right? Your C can be converted to the per unit, all right? Now you can see that from the previous calculation, the 4 plus J7 ohm is equivalent to 8.0622 and angle of 60.25 degree. This is the actual value divided by the base, which is 33.33. That becomes 0.2419 and angle of around 60 degree, and this is in PU, right? So I just computed all the circuit quantities in percentage or in per unit. Okay, now you can use your the voltage equation, right? You know that the Vs, okay, Vs is equal to VR plus what? I times Z. Okay, the original equation in this the last computation I show you was that the VI is in kilovolts and this is in kiloamps times this is in ohms. So now if it is in per unit, right, everything it must be in per unit, okay, PU, and everything is in PU. I want to put this in PU, everything is in PU. So you can try, right, VR here is 1 angle of 0, 1 per unit, times I, which is 0.866, angle of 36.9, and multiply by, okay, this is the voltage drop terms, multiplied by 0.2419 and angle of 60 degree, right? If you hit the calculator, okay, you can try to hit the calculator, you will get a certain amount x per unit, okay. Now I need you to do this by yourself, and you would appreciate the method, right? Hopefully you would appreciate it, but I would just leave this to you. You compute these numbers, and when you want to compare with the previous calculation, right? I want to reconvert, right? I have to convert this per unit quantity back to the original value, right? I want to compare whether or not it is equal to the value we already computed, which was 6.9 angle of 3.982, right? Now the thing is, you get the percentage, right? And you want to change this value to be how much in kV, okay? What you have to do is that you just multiply this back by the base quantity. In this case, you see, this is the Vs. Vs is the voltage, right? So after you know the Vs in per unit, this is to say what? This is to say that how greater of this Vs compared to the base quantities. For example, let's say if you get 1.5 per unit, for example, what is an interpretation of this? Okay, it is 50% greater than the base, right? This is the 1.5 per unit means that this is greater than 50% greater than the base quantity. If my base is, for example, I just take the simple number, okay? If I have the base of 10 kV, okay, how much is the voltage of 1.5 pu, okay? So 100% or 1 per unit is 10 kV, and I have 50% greater than the base, so I have 15 kV, right? So basically what? This is 15 kV, this 15 kV comes from 10 kV times 1.5, right? So by converting this to the original value in kV, you have to have this xpu, you have you should get this xpu, you get xpu, then you multiply this by 10 divided by root 3, which is the voltage base, right? And you must get the same or almost the same value as this guy here, okay, this guy here, all right, because this is the same network, okay. If you do it right, then you should get the same, almost the same figure, okay. You, of course, the number can be different because of the round-off error that you have made during the calculation, okay. But those round-off error must be not too high, okay. So I will stop this example here. I hope you get something out of this clip. So thanks for watching.